Welcome to Chapter 4. In this chapter, we're going to talk about energy and global temperatures. So these are the terms for this chapter. We're going to start with looking at what energy really is in terms of electromagnetic spectrum. Then we're going to sort of simplify the electromagnetic spectrum into shortwave and longwave energy. Look to see how the Earth as a whole tries to maintain something called an energy balance. Then we're going to get into concepts such as albedo, insolation, talk more specifically about what temperature really is, specific heat, wind chill, and more. So to start with, as you already know, the sun is the primary source for the Earth, and especially for the Earth's atmosphere. Now, we talked a little bit about the sun back in chapter 1. It's really an average-sized star. Nuclear fusion is what keeps the sun or most stars going. The energy coming out of the sun is intense the closer you are. So it just so happens that the Earth is a really good distance so that the energy can spread out and give the Earth enough energy to sustain life. All right, so to start with our talk of energy that comes from the sun, we need to discuss electromagnetic energy. And we're just going to look at a piece of that energy, which is the visible spectrum. And that visible spectrum is basically the colors, the different colors that we see. For example, red, the color red has a longer wavelength than violet. And because of that, we see those different colors. Now, red has a long wavelength, we can say, while at the same time, violet has a short wavelength. And so you might want to think about which one has more energy. Because this is light, it's traveling at the speed of light. There's a lot more waves that are traveling by you when you have a shorter wavelength than you have longer wavelength. So in this very simple example, you could see how longer wavelengths of any kind of radiation tend to be weaker. They don't have as much energy associated with. Whereas shortwave energy, such as this violet color, has a much more powerful effect, especially when we get into something a lot more energetic, such as cosmic rays, gamma rays, and ultraviolet rays. So this shows you the full spectrum of the electromagnetic spectrum. Up here we have ultraviolet, or sorry, we just have violet, which is 0.4 microns, and then we have 0.7 microns for red. Those are the wavelengths. A micron is a millionth of a meter. Now, if we looked at the kinds of radiation that we actually can't see with our eyes, we can go all the way to the extremely short and extremely dangerous cosmic rays and gamma rays. These wavelengths are extremely small. This is 0.000001 micron, which is really 10 to the negative 14th meters. All the way to the other end of the spectrum where we have long radio waves and AM radio waves where sometimes the wavelength is just 1,000 meters. So we have everything in between. What we'll learn is that we're going to look at the different types of energy that come from the sun, and believe it or not, energy that comes from the earth. Yes, even you sitting there listening to my lecture, you are emitting radiation. So we're going to demystify a little bit of what radiation is. It's not just this nuclear radiation that you hear about, which nuclear radiation might fall into the high energy short wavelength category. There is a lot of other types of radiation. So we can boil down these types of radiation into two kinds. The kind that comes from the sun and the kind that comes from the earth and all of the things that are part of the earth, which include you, people, cars, buildings, whatever. The highest concentration of energy that comes from the sun falls within the ultraviolet and visible spectrum. And we could just simply call that shortwave. And so with these slides, you will notice that some of these waves are yellow and they're shorter. So that will symbolize shortwave energy coming from the sun. The Earth, because it's much cooler than the sun, it emits longer wavelengths, typically in the thermal infrared spectrum, part of the spectrum. So there's a correlation here. The hotter something is, the more energy, the more radiation it will emit, and that radiation tends to be of a shorter wavelength compared to a cooler body. So we have an energy budget here. We have the energy that's coming in, we call that input from the sun, and an energy that leaves the Earth, and we call that output. And in order to maintain the same types of temperature or the same range of temperatures from year to year, we have to make sure that this is balanced. But it's not always balanced. And we could talk about that in the short term, and we could even talk about this balance in the long term, especially in light of climate change. So we're going to get a little bit more specific now, and we're going to talk about what happens to these two types of radiation. So as you know, we have energy coming from the sun, and we call that shortwave radiation. Now, not all of it actually makes it down to the surface. Much of it is reflected by clouds and by lighter colored objects at the surface. Some of it is diffused by molecules or particulates in the atmosphere. So much of it is reflected back to space, and I'll tell you exactly how much that is in a little bit. So bottom line, not all of it, but about half, roughly half of the sunlight makes it down and is absorbed by the surface of the Earth. Once it's absorbed, then because of the Earth's cooler temperature, luckily the sun doesn't heat the Earth up to the same temperature the sun does. So some of that energy is lost. And so we have a cooler planet, cooler than the sun is at least, and it emits longer wavelength. Some of that is in the atmosphere. Some of that is at the surface. But what happens is that a lot of that radiation wants to escape toward Earth. But this little, what looks like a hat, represents something in the atmosphere that prevents all of the Earth's radiation from escaping all the way to space. And that is greenhouse gases. Now you might be thinking, wait a minute, greenhouse gases are bad. That's not true. Too many greenhouse gases or too much of a concentration of greenhouse gases can lead to a warmer planet. But thankfully, our atmosphere has greenhouse gases that absorb this long wave radiation and transmit it back down to the surface, and that keeps us warmer than otherwise. Compare that to, let's say, the moon. The moon doesn't even have an atmosphere. Therefore, it doesn't have any greenhouse gases. So any kind of energy that is absorbed by the sun, once the sun goes down, all that energy escapes right out to space and you would freeze to death. So essentially, these greenhouse gases, which include, as I said before, carbon dioxide, water vapor, methane, they actually help keep life-sustaining temperatures on Earth. Of course, the problem is we don't want too many of them. So the factor that I talked about that I alluded to in the previous slide is that not all of the sun's radiation even makes it down to the surface of the Earth. And if it does, a lot of it gets reflected right back to space. If you're dealing with fresh snow, up to 95% of that radiation is just reflected and not absorbed. However, let's say that you're dealing with a hot sunny day in fresh asphalt. That asphalt, because of how dark it is and some of the chemical or the physical properties, may only reflect 5%. So depending on where you are and the types of material and the color of that material, that'll affect what we call albedo. Albedo is the reflection or the amount of reflected sunlight that goes back towards space. Generally speaking, if you're in an area that has a lot of grass, you will have much higher albedo than asphalt and concrete. Now, there's a lot of material that's on the surface of the Earth, so really the only number that I want you to know and keep in mind is Earth's average albedo, which is about 31%. The other very important thing when it comes to both albedo and greenhouse, we'll say forcing, are clouds. As you probably already know, when it's the daytime, clouds will keep the surface temperatures cooler. But at night, maybe you haven't realized this, but at night, clouds will actually help warm the surface of the Earth than if there were no clouds. So it makes more sense, let's start on the left here. It makes more sense that clouds keep the Earth cooler during the day. Clouds reflect sunlight, keeps some of that sunlight from getting to the surface of the Earth, so therefore daytime temperatures are cooler. What happens at night though, if we have a cloudy night? Think about the marine layer that happens to form in the evening hours during the early summer months. We have clouds that last until the early morning. Those nights, especially along the coast, are relatively warm. That's because greenhouse gases actually are absorbed by these clouds and then radiated back toward the surface of the Earth. So clouds are like heaters. They heat the surface of the Earth. Now take another night, let's say it's completely clear, and this is most noticeable in the winter time. Surface temperatures will drop quite a bit. And in the valley, in the San Fernando Valley, we see that much more. Cloudy nights versus clear nights in the wintertime will have a much bigger difference in temperature. In fact, this is a map that I like to show to get some spatial analysis experience. So we're looking at the world here, the entire world, and I'm highlighting a specific part of the world right here. We call this the tropics. Now, from previous lectures, you might think, okay, well, we have the sun's strongest radiation typically hugging the equator. But my question to you is, this map is showing you how much energy is received at the surface of the Earth. Why don't we see that very strongly around the tropics? And if you don't know the answer to this question, think about what kind of features, land features, you would find in the tropics. We have the Amazon rainforest in Brazil. We have rainforests in Central Africa. What causes those rainforests? Clouds and rain hug the equator, and they prevent a lot of the Earth's solar radiation, or something we call insolation. It prevents it from being received by the surface of the Earth. What we do see, where we see a lot of insolation, is in our deserts. Our deserts where we have a lot of sunny days. So we have the deserts of North America, the Sahara Desert, and we have the outback in Australia. Those are just a few of the deserts we see around the world. They have a lot of sunny days and a lot of incoming solar radiation or insolation being received by the surface. So before I talk about the full energy budget, we have to talk about various heat transfers. The one we just discussed was radiation. It's energy that travels in waves. Let's say you're boiling a pot of water, and you don't have a handle that is nicely insulated. When you touch that handle, especially if it's metal, it'll burn you. You would drop the pan. So up here I have what we call conduction, a molecular view of what conduction really is. It's a molecule by molecule transfer of energy. Let's say you're boiling a pot of water and you see parts of that water rising up to the surface in the form of bubbles. We call that convection. So we have conduction, molecule by molecule. We have convection, and we have radiation. Convection is mass movement of fluid. It happens in water, And it happens in the atmosphere as well, as I'm highlighting down in the lower left. Masses of air that will rise. Actually, I have it going the other way. But we're going to talk about latent heat in chapter 6, but just keep in mind that's also a way of heat transfer. It's basically by evaporation or condensation. So there are various ways the atmosphere can get warm. So this is a quite complex figure. You won't see this in your book. You may see something similar to this. I'm going to break it down little by little, and there's only a few pieces of this that I really want you to know. So let's say we're starting with 100, we'll say percent, 100% of the sun's energy. It's reaching the top of the atmosphere. But 21% of that is reflected by clouds. 7% is being diffused through scattering, and 3% is being reflected by the surface through albedo. That leaves 31%, which is a number I already asked you to remember, of reflected that the surface and the atmosphere doesn't even bother dealing with. The rest of it, we have 20% that reaches to the surface through diffusion, 25% directly, and we have 18% absorbed by atmospheric gases and dust, not very much. We have some of it absorbed by ozone as well. All of that is absorbed and then you could think of it as being re-emitted again by the surface through long wave, whether that's directly by the atmosphere or by the surface. By the way, which one is more, the surface or the atmosphere? The surface is more. Believe it or not, when you go outside and you are warm, it's not because the atmosphere is getting directly heated by the sun that much. It's really because the surface of the earth is getting heated, and then that heat is rising up. How does it rise up? It rises through convection and some latent heat. Don't worry about the numbers down here. And some of it, as it's rising, gets quote unquote trapped. Now, I don't really like to use the word trap because a greenhouse does trap heat in, but greenhouse gases actually absorb energy, long wave energy that's escaping towards space, and then when it absorbs it, it re-emits that energy back down to the surface. That's really what the greenhouse effect is. And some of that energy does go all the way out to space, but notice here that in a perfect world, all the energy that's coming in, which is, we have 31% that's being reflected, so we have 69% that's actually being absorbed, okay? And all of it goes right back out to space. So in a perfect world, we have a balanced budget. Now we're looking at a global view, okay? Now specific areas across the Earth may not have a balance, but overall it should all balance out. But if we also continue to look at this globally, if we increase the number of greenhouse gas emissions, we will increase the Earth's temperature. And this is something that climate scientists are still looking at and trying to figure out exactly what is causing our warming temperatures. So we're going to go into a little bit more specific about how temperature changes from place to place. Before that, I want to talk about temperature itself. You may not have really thought about the true definition of temperature, but really temperature is the amount of kinetic energy developed by something by its molecules. So your molecules are all vibrating and moving around a little bit at a certain rate. The average rate of movement, we're not talking about mass movement of molecules, we're talking about like vibrational kinetic energy on a molecular level. The higher that average is, the hotter the temperature is. And theoretically, if you use the Kelvin scale, if you go all the way down to 0, which is not even shown on here, that's absolute 0. We have 0. 0 Kelvin is absolute 0. That looks like okay, but it's actually 0 Kelvin. We don't use a degree symbol for Kelvin. That's only theoretical, but by then, theoretically, all the molecules would just stop moving. In the United States, we're used to the Fahrenheit scale. And just to give you sort of a range here, normal room temperature is about 68 degrees. Boiling is 212 degrees Fahrenheit. And freezing is about 32 degrees Fahrenheit. Celsius is used in science a lot more along with Kelvin. And it's nice because Celsius has 100 degrees as boiling and 0 degrees as freezing. So I may go back and forth between Celsius and Fahrenheit. I probably won't use Kelvin in this course. Notice something interesting. Negative 40 degrees Fahrenheit is the same as negative 40 degrees Celsius, because both of these temperature scales are arbitrary, and so they just happen to coincide at that temperature. Kelvin, though, puts 0 at the minimum, which is nice when it comes to science. So what we're going to do now is, instead of looking really globally here, we're going to go more specific into local regions and what exactly controls temperature. And these are the 4 primary controls of temperature. There are other ones, but these are the ones we're going to focus on in this course. We're going to look at latitude, which you already know what that is, but that latitude is linked very much to insolation. We're going to look at altitude, land and water, sea, or land and sea interactions, how that actually will influence temperature, and ocean currents. But this slide, I want you to just remember that the most important control of temperature is latitude. Why is that? Okay, we talked about how much energy there is at the tropics compared to the poles. We did that a little bit in chapter 1. And also, we may have hinted a little bit about it in chapter 3. Basically, we have this whole region here that has so much more energy, even though there are clouds that are blocking the sunlight at the equator. We still have a lot more energy at the tropics than we do at the poles. In fact, we have an energy, we have positive energy, we have a gain in energy at the equator, so much so that some of that energy has to be transferred to the poles because the poles have an energy deficit, both of them. The whole reason why weather even occurs is because of this difference in energy between the tropics and the poles. So the way I want you to remember this is that the lower the latitude in general, given that all other temperature controls are out of the picture, lower the latitude, the warmer the temperature is. So we have 5 different cities. And there's something else I want you to know when it comes to latitude as well. So let's take 2 cities that I haven't been to necessarily. I haven't been to Barrow, Alaska, but my family has been to Barrow, Alaska. And then I have also been to New Orleans, Louisiana. Let's compare these 2 cities. Now, Barrow, Alaska is 71 degrees north, pretty close to the poles, or to the North Pole. New Orleans is much closer to the equator. As you can have guessed, in the summer months, which are June, July, and August, right here, you have warmer temperatures. And you have cooler temperatures in the wintertime. Barrow, Alaska, much cooler temperature, overall much cooler temperatures. But look at the difference between summer and winter. A much larger difference in temperatures from summer to winter are usually found in places that are at high latitudes. So not only do we have colder temperatures in Alaska, we have a bigger difference between summer and winter. Just take a look at Salvador, Brazil, much closer to the equator, 13 degrees south. You hardly ever have a difference in temperature. Why do you think there are slightly cooler temperatures during June, July, and August? If you've guessed that because in June, July, and August, the Southern Hemisphere has winter, you are correct. Of course, that's not much of a winter for Salvador, Brazil. Altitude is a pretty easy temperature control that we can think of. Basically, okay, so first of all, we have 2 cities here, Concepcion and La Paz. They're both in Bolivia. They both have very similar latitudes, 16 degrees south. However, the elevation of Concepcion is about 1,600 feet above sea level. However, La Paz is over 13,000 feet above sea level. So which one's colder? La Paz. Because of its high altitude or elevation, it has consistently colder temperatures than Concepcion. Now, the one control of temperature that you might have to get used to a little bit is the difference between land and water. On a physical or chemical basis, land has a low specific heat. A low specific heat means that it takes a lot of energy for land, or I should say, actually, it doesn't take that much energy. I was thinking of water. It doesn't take that much energy for land to heat up very quickly. But that also means that land can also cool down really quickly. Water has a high specific heat. It takes a lot more energy to heat up water. So what that means is, if you are living in an area that is surrounded by a lot of land, not much water, you will have much faster changes in temperature. You'll heat up really quickly, but you can also cool off really quickly. If you are in an area next to a large body of water, whether it's a large lake on the coast of by the ocean, if you're on an island, you will have much more muddled temperature changes. You will not see much changes. So that also kind of explains why, let's say you're in Malibu during the summer and your temperatures are, maybe 70 degrees during the day. But if you go out to Palm Springs during the day in the summer, you'll have temperatures well over 100 degrees. Also, let's stick with these two places. Let's say you have wintertime temperatures in Malibu. Wintertime temperatures at night might be down in the 60s, maybe 50s. In Palm Springs, you could get down into the 30s. Landlocked areas are definitely have a large temperature change. The other thing that can really play a role is the temperature of an ocean current. This plays a big role in the summertime for the United States. Areas along the East Coast tend to have a lot more humidity and can be much warmer, actually, on the coast because the Gulf Stream is much warmer. I don't have a picture for this, but if you live on the coast of the West Coast, right on the coast of California, we have the California current, which is very cold compared to the Gulf Stream, and therefore the temperatures right on the coast can be also much cooler. So to put these two temperature controls in play, we have two cities, San Francisco, which many of you probably have been to because it's much closer. It's at a latitude of 37 degrees. We also have Wichita, Kansas, same latitude. The elevation is not much different between the two. What's different is that San Francisco is along a cold body of water, relatively cold, where Wichita, Kansas is almost in the exact middle of our country. As you can guess, the summertime temperatures in San Francisco are much cooler than the summertime temperatures in Wichita, Kansas. However, the wintertime temperatures of San Francisco are warmer than those of Wichita, Kansas. So Wichita, Kansas has a much larger difference in temperatures between summer and winter, especially compared to a coastal city like San Francisco. So what I want to do now is I want to show you a map, and I want to take two specific temperature controls and use some spatial analysis. We're looking at air temperatures, not water temperatures, but air temperatures in January. And as you can tell, or hopefully you can tell, we have much warmer temperatures in the southern hemisphere than we do in the northern hemisphere. One reason is it's January, so it's summer down in the southern hemisphere. Now, where do you see warmer temperatures in the southern hemisphere? Over land? By the way, this is South America, this is Africa, and this is Australia. Or do you see warmer temperatures over the water? I see warmer temperatures over the land, which makes sense, and I see at 30 degrees. By the way, this is in degrees Celsius, so that's about 86 degrees Fahrenheit. I see much warmer temperatures over the land than I do over the water. And on the flip side, if you go up to the northern hemisphere, I see much colder temperature values over the land pieces. We have Greenland and we have Siberia than we do over the water. Now let's change to July. Now July, we have a huge change in temperature. So July now is summer in the northern hemisphere. We also see the warmer temperatures over the land. We see warmest over the Sahara Desert. Down in the southern hemisphere, we see the coldest over land because it's winter down there. I see -60 down over Antarctica. By the way, which hemisphere has more land, northern hemisphere or southern hemisphere? If you guess northern hemisphere, you're right. The southern hemisphere, almost 80% of it is covered by water. So in general, the seasonal differences in the southern hemisphere are not as great as they are in the northern hemisphere. Here's another way of looking at it. This is an annual range. As you can tell, some of the most landlocked places in the world, in the middle of North America, and close in the high latitudes, and in high latitudes of the Eurasia continent, have some of the greatest temperature ranges. Whereas areas that are near the tropics and over the water barely have a temperature change. Okay, so the last part of this that I want to talk about, I just want to talk a little bit about wind chill and urban heat island effect. And so basically what these two concepts do is that what they're trying to get at is that the human body is not a very good sensor for temperature. When it comes to really cold and really windy conditions, our bodies will feel colder than what the real temperature is. Also, what I don't have on here, which we'll talk about in chapter 6, is what happens when there's a lot of heat and humidity. And then we'll talk a little bit about what humans do to the environment through urban heat island effect. This is a chart that tries to show what the apparent temperature is when you deal with temperatures that are cold. You know, we're talking temperatures from 50 to -40 degrees Fahrenheit, and when the wind speed is very high. Living in California, unless you're a skier, you may not have experienced these kinds of temperatures. But let's take something that I experienced growing up living in Chicago. So we're going to take a temperature of 15 degrees and a wind speed of 40. The apparent temperature of that, if you use this chart, is -8 degrees Fahrenheit. Now, if you do something a little bit more severe, like in Antarctica, you might deal with the temperature down at, like, I don't know, maybe -20. And in the wintertime, the wind speeds can be very strong, we'll say 70. If we do that, I'm trying to follow it along here, it looks like you have a wind chill of -64 degrees. And this is in a very dangerous zone here. It would only take 5 minutes for your skin to become frostbite. And don't worry about this equation, but this equation down here is sort of empirical equation that we've used to estimate these values. Bottom line, when it's really cold and really windy, it'll feel colder than what a thermometer would actually read. This is a typical weather map you might see on the Weather Channel, and it shows you not what the actual temperatures are, but what the wind chill temperatures are. As you can see in my hometown here, we had a wind chill about, I don't know, a few years ago of -4. That's very cold. I do not miss that part of the weather out there. And then something else that happens when you live in a large urban environment. Concrete, cars, pollution, dust, it creates like a dome. And during the day, and definitely notice it at night, it keeps the temperatures warmer than if you were out in the middle of farmland or desert. And we call that the urban environment or the urban heat island effect. And basically, the larger the urban area, the warmer the temperatures will get. And part of it's because of how much of the sun's energy is being absorbed by buildings and concrete. It doesn't take much. This graphic here shows a very modest city. We've had studies saying or showing that cities as small as 40,000 people can actually have a change of temperatures within the main part of that city. So in this case, we have a downtown area, and we see the urban heat island effect. Temperatures up to 92 degrees. Compared to areas that are much more rural, let's say around a river, where daytime temperatures may be only 80 degrees. So it's a huge difference. In fact, when I look at the weather, or actually the Pierce College Weather Station, I look at the temperature patterns from the late 1940s, which is when we started recording temperatures, to this century and even this decade, I see a large difference. Some of that is global climate change, but a lot of it is because Woodland Hills used to be much more rural and agriculture, especially back in the 1940s, compared to today, which is a lot more urbanized.